what I want to do next is ask a very important question. Remember, we're now done some observations and we want to model them. And modeling means, how do I generate this? How do I generate this behavior? What does generation mean? What does it mean to generate something? Okay. What does it mean to generate a trace? Okay. Identify some set, let's call it X, start from some point at X, and apply a function F, capital F, okay, and that takes you another point. So you start with X or X naught, you go to F of X naught, you go to F squared of X naught, you keep applying F. So notice from X, you've gone to another value, not from the index, not from N. From X, you've gone to X. The trace was taking you from N to X. Now you're actually going from X to X. So locally, if I'm in here, where do I go next? It's a local description of what's happening. That's the key idea in all of this. The key idea is, what is that generative mechanism, right, from which I can actually produce the trace that I'm seeing. So if you start, so I'm just writing down the terminology, that just going to assume that you'll get it eventually. These are just words after all. Okay, so a map F takes you from X to X dash or X prime. Okay, and if you start repeatedly applying it, you get a sequence X naught, F X naught, F squared X naught, and so on. That's called a trajectory. That's a trajectory of X naught. Okay, from the trajectory, I need to get the trace. Correct. So let's just work out simple examples before we get to more complicated examples. And remember where we're trying to go with this. We're trying to see how programming and algorithms can be put in this framework where we can think of traces first and then think of how those traces are generated. Right? That's the idea. And we will get to programs. We will build programs based on these ideas. Okay, so very simple. So evens, instead of saying, you know, if I give you the ith index, it's 2 times I can say, if you give me X, whatever the value of X is, I can just add 2 and get the next one. Correct? Okay, so note it's a different kind of behavior. This behavior, if I start with 0 and this F, I can keep applying F and I can recreate that sequence. Correct? Agreed? Okay, if you have questions, can one of you try to see if there are questions on the channel? Like,
yeah, there are.
Okay, yeah, good. Okay, so similarly for the other examples, right? So you are at a particular value. How do I get the next value? That's the game. In fact, in all of programming, that is the game. Okay, or all of algorithms in some sense. Okay, so. Oh, is that a mistake?
No. I think it's just a question.
Yeah, I think it's, I'm not sure. Yeah, okay. So take the traffic light, right? So if the light is red, where should it go next? If the light is yellow, where should it go next? And so on. Okay. Now let's look at some other examples. So I'll give you an example like that. The first one, let's just look at the first one. Ignore. I mean, there are a bunch of other examples. Let's just look at the first one. It says squares, right? 0, 1, 4, 9, and so on. So as a trace, what's the trace? How would I describe the trace? I goes to I squared, right? Simple. Okay. But now suppose I want to generate that trace. What do I do? How do I generate this trace? You want to think about it for a moment?
Generate, you mean from the current one?
Yes. I want to be somewhere and go somewhere so that the trace takes me from 1 to 4 and 4 to 9 and 9 to 16 and so on. Okay. Let me give you a hint. Okay. Think of this sequence as simulating the distance traveled by a ball when you drop it from a building. So the height from the top of the building where the ball is that distance. And just imagine this some infinitely long building and you're just dropping it. Okay. Does that ring a bell? Does that ring a bell?
Add odd numbers too.
Sorry?
Add odd number 1, 3, 5.
There you go. Okay. So what you're seeing, that sequence of numbers could very well be the distance that the ball is traveling. Correct? And when would that distance change quadratically or behave quadratically? Under constant acceleration, the thing would move, the velocity would linearly increase. So in order for me to explain, I don't have a picture of this, but we've all done this in high school. So I presume we don't need a picture for this. Okay. You can imagine the velocity is changing linearly. Okay. Velocity is linear. The acceleration is constant. Okay. So in order to explain the distance, how the displacement is changing, I need to have information about velocity. Okay. Simply by looking at those numbers and trying to manipulate one variable, I'm going to get myself in loops. Okay. In order to explain, which means generate this behavior, okay, I'm going to have to do something that is different. I'm going to start manipulating two values that are changing in a certain pattern. I've not told you what that rule is yet. Okay, but you can just look at it and guess it perhaps. And notice that when I project one of those values, I get the sequence that I want. So the sequence you're seeing called the trace is somehow derived from a trajectory. Okay. The trajectory, when you project the right components, gives you the trace. Okay. So the trajectory consists of a sequence of states. The trace consists of a sequence of observables. Okay. You're observing the distance, but you're not really observing the velocity. But it's there, it's part of this change. And once you account for that, then it becomes very easy for you to explain how the sequence changes. Now, you may very well be able to explain it without that. Maybe there's some other very clever way of doing it, and I don't know about that. But this is, remember, we're looking at explanation. There's no unique way to explain something. Okay. So if you think about this example, okay, we've got this state space X, and we've got this observation space Y, and we took the function H, the map called H, the display map that took you from the state to Y. Notice I wrote that in this previous slide. You can see the H is taking you from the state to the trace. Okay. Okay, now you should start seeing how these ideas connect with programming. Think of display as a print statement. Think of state as all the variables in your program. They're all changing together. There's some rule, which is literally the logic of your program, that is manipulating these variables. And one of them you have printed out, one or a couple of them, you printed them out. Okay. So the function H is nothing but print. Of all these variables, pick one and print it, right? That's what H is. Okay. So I'm trying to connect it with where we want to go eventually. We're not there yet, but with programming. Okay.
Isn't H more like a program itself?
No, the H is more like a print statement. So the question is H the program? The H is part of the program. And in fact, H is sort of easy to explain. It's really, you've got all these program variables, right? But you're actually observing or you're tracing only one of them. You're not necessarily tracing all the variables of your program. You're tracing the variable of interest. And I'll explain what that of interest is. It's the variable that's going to eventually hold the answer.
Okay, so I can see that the output of H is perhaps what gets printed or what you
Yes,
see. So
yes.
in that sense, H is
Yes,
print
yes,
function.
right.
But if it's mapping all possible configurations of
No,
your
it's
internal
saying that
program?
if you give me a bunch of variables,
Right.
I'm going to print one of those. Think of it as a component X. Think of it as a projection function. Just project something.
Okay,
got a-
I mean, I was imagining that the observation space Y could be completely disjoint from the state space X.
Yes,
So-
not necessarily. That's the point.
but
Not
if it-
necessarily. In
if
fact,
it-
the observation space is often embedded in it.
So if it's embedded, yeah, so I was thinking that if it's disjoint, then the projection was not, it
No,
wasn't clear to me how it's a
think
projection
of y as a component of x.
as a component of
Yeah.
X.
Component, not subset. Okay, we'll see examples. We'll see examples of this. So here's the squares problem, right? So what you're seeing on the right-hand side of the screen, this stuff here, right? You see that, sorry. Right, that's your trace. You see that? On the left-hand side, you see the trajectory. To be precise, the trajectory of 0, 1. Correct? The thing connecting the trajectory to the trace is this function h. Okay. Now, we're trying to solve the squares trace, right? We're trying to explain the squares trace. The way we're going to explain it, there's an observation space with just numbers, and there's just natural numbers 0, 1, 2, 3. But the state space has two components. Okay. And what the two components together are called a vector, state vector. And I'm just going to give them names so it's easier to refer to them rather than x0 and x1 and so on. I'm just going to call them v and d. Think of v as velocity, d as displacement. Okay, and the initial velocity, initial displacement is 0, but the initial velocity is 1. And everything is discrete here, just to make things extremely, extremely simple. So what does the display map do? It literally displays to you the position and not the velocity. You're just taking v and d, just giving you d. Okay, the interesting thing is what is happening in that map. Right? How do the two values change? Well, it's constant acceleration, so v goes to v plus 2. It could go to something else, it could just be a, but let's just pick 2 for now because we want to simulate that sequence, right? And the new displacement is the d plus the distance traveled in 1 unit of time, which is just v, right? So the new value of d prime is d plus v, the new value of v is d plus 2.
Why is it called squares? I probably missed some part.
Because it's when you look at the displacement, it goes 0, 1, 4, 9, so on.
Okay.
Okay, so you're looking at this behavior, which is just squares, but if you want to generate that behavior, you get an extra variable, you don't need squares anyway. In fact, you just need addition, you don't even need multiplication. Okay, so the pattern that you see, the trace that you see, the behavior that you see, okay, oftentimes trying to explain it could involve more things, more moving parts. Okay, that's one of the key ideas that you're taking from dynamics, okay, and we want to apply it to programming. Okay, the analogy is very clear. The state is nothing but the set of all program variables that you have. Okay. The observable is the variable of interest, perhaps the variable carrying the answer, which you want to return from your program, right? That's also a variable, right? Typically, you just return a variable. Okay, let's assume that is the one we're interested in, okay? Okay. Here's another example, another very familiar example called factorial, right? So I have the sequence 1, 4, 12, 24, 24, 24, 24, 24, and so on. Okay, it seems to be stuck at 24. Okay, no problem. Let's just go on. Okay, how would I ever generate such a trace? And this is a trajectory of 4, 1. Okay, so I start with an observation space, which is natural numbers. State space again has two values, n squared. Examples are trivial here. Okay, I've deliberately picked very, very simple examples so that we don't waste our time trying to figure out what is this new example. Okay, we just want to see that the vocabulary we're learning, the concepts we're learning are applied on extremely familiar examples. So we don't have to juggle two things changing at the same time. Okay, so again, the state vector has two variables, I and a, right, two quantities. And the initial value of the state x naught is 4, 1. And again, I'm extracting the second value. Okay, you can think of a as the accumulator or the answer in this case. Okay, and what is a map? This is the kind of program we've written hundreds of times, many years ago, in all kinds of situations. Factorial. We know what the factorial function looks like, and you can literally translate this into code in no time. This is practically code for all practice, right? Okay, different languages will have slightly different syntax, but you can see what's going on. Okay, and we will write this code. We'll work with this example all the way. Okay, so any questions? Anything? There are some exercises coming up, and we'll pause on those exercises. I think they're about to come up. Okay. Okay, so this is a summary. This is sort of the conceptual vocabulary that I want to set up before we start looking at other aspects. We've got an observation space Y, we've got a state space X, we've got traces that map you from, remember, everything is in terms of maps. Okay, this is a bit like functional programming. Everything is a function. Okay, so we want to think in terms of maps. Right? Something, a function or a map takes a value from one domain and gets you to another domain, a value in another domain. Okay, and it's a function. So you have a trace, which takes you from, give it a number, give an index, it'll give you a value in Y. The trajectory takes a value in X and then builds a trajectory from there, builds, a sequence from there, correct? So trajectory of a point. You're going to call elements of X points or states. We're going to use that interchangeably. The display map we've already seen. The dynamical map takes a point in X, maps.
Venkatesh, question. Am I wrote a question? Hello?
Yes.
Yes. So, would it also make sense to have a function that tells when to stop or when to produce an output? Like in your factorial example.
Yeah.
Rather than yes. So, wouldn't it be in a sense more natural to start with 0, 1, and then 1, 1, 2, 2, 3, 6, etc., and then have some other function which tells you when to stop and produce an output?
Okay. The question is, when do I stop? Is that right?
Yes. Yes. Yes.
Yeah. So there is, interestingly, a universal criterion on when to stop. And we will simply appeal to that universal criterion in this framework. And you're going to see it in just a moment.
Okay. Okay.
Yeah. So I will definitely get to that, because if our programs don't stop, then we have a problem. Right?
Okay.
Yeah. Okay. So this pair, the state space and this dynamical map together, are called a discrete flow or an iterative system. Okay. It's an iterative system because it lets you iterate using F on that space X. Okay. Now, this is typically not the vocabulary that I would be engaging with as a Python programmer or a C programmer. Okay. But I'm hoping one day that we will all do that. So my goal is extremely ambitious. My goal is to see that this is how we teach programming. The students are coming in. By the way, these students are also doing engineering and science. Let's not forget that. So let's leverage whatever they're studying in science and engineering, as you were saying, to teach them computing and teach them programming, no less. Okay. So it's not just learning the syntax and just getting in front of a computer and coding. Of course, there are lots and millions of people who do that, but I'm looking at this set of people who are smart, who have a background in engineering and science, who are studying it together, and how do we leverage that in the programming education? Okay, so the first is we introduce, by the way, this vocabulary that I've introduced has nothing to do with programming. You will find this vocabulary in physics, you will find it in engineering, you'll probably find it in systems biology, you'll find it in all economics, you'll find it in lots of places. People talk about state spaces, people talk about fixed points, people talk about observations, traces, trajectories, so on. Okay, so this is a very, this probably would be called system science, this ability to describe systems of all kinds. Okay. Okay, so here's your chance at an exercise. Okay. Now, just wanted to remind you that there are many ways you can do the exercise. You can just grab a sheet of paper, write it if you like, but on the group, on the WhatsApp group, there is an opportunity for you to look at a Python notebook, make a copy of it, and if you're in front of a computer, just typing there. Okay. Mrityunjay, did you want to add something about that? I have my colleague. Okay, so it's already been posted or it's in the process of being posted. Yeah. So your first exercise, I would say, would probably take 5 minutes. Just cook up 2 simple examples pick any observation space and just do a trace, just define a trace. Okay. Your observation space could be numbers, it could be real numbers, it could be whatever you want, it could be chairs, it could be whatever it does. Okay. And then try to see if for that trace that you have, can you define an iterative system? Can you define a rule that will generate that trace? Okay. And can you have a trajectory? So now that rule is going to actually generate it. So you need a state space, and the rule is generating the next state. And so therefore you get a trajectory. And from that trajectory, how would you get the trace? Which means you need that function h, the function that projects. Just any, you can cook up anything you want. If it's trivial, no problem. Just do it. I mean, just cook up whatever comes to your mind. Something very, very simple, or you could take whatever you want. It could be, just see that it satisfies, it sort of aligns with what we've just looked at. Right? This is just so that you can engage with that vocabulary, you can get comfortable with those. Okay. And if you have questions, just raise your hand here in the physical classroom, or just put out something in chat. We're following you there as well. No, if you want to type a program, then you can, but if you want to write, you can write there. If you don't have a sheet of paper in front of you and just want to write, because that collab sheet will let you just let you type out things. Yes, people want the link. Yes, we will get the link for them. Okay, while you're doing this, just write things down clearly. Here is the observation space. Here is a trace on that observation space. Here is a state space. Okay. Here is a dynamical map, and this dynamical map with this initial value of the state will generate this trace. And to get from that trajectory to the trace, here is a function h that takes me there, right? All the pieces. I'll give you, just for your own benefit, I will also show you this little example where the whole thing is done for factorial. Right? Can you see that? You want me to put this example here so you can see what's going on? Cook up an example, an observation space, a trace, okay, a state space, state vector, a map, and the dynamic map. Yes, please.
Can y be n cross n?
Y can be anything you want, absolutely anything you want. Absolutely anything you want. Take anything you want. Real numbers, complex numbers, it could be pictures, it could be whatever you want. It could be strings, maybe you just work with strings. Right? Maybe you could work with booleans, Boolean strings, arrays. If you want examples, I'll go back to my previous slide. Here, look at the examples. Look at these 4 examples, okay? And see what are the different, in the first case, you can guess perhaps that the observation space is just natural numbers. In the second case, you can also natural numbers. In the third case, also natural numbers. But in the fourth case, it's actually arrays. So you're observing an array getting transformed somehow. Okay. Now, how it's getting transformed is a mystery that you want to solve. You want to be able to explain, why is this array 8697 getting changed? How is it getting changed? And can I explain that? That is science. The ability, the effort in trying to explain a phenomenon, right? Captured as a trace or a set of traces. Why do I say a set of traces? Because you don't want to just give the answer for this particular sequence, right? That'd be quite useless. I mean, you want to do this, generalize it a little bit. So you want to take, hey, any array or any initial value.
It's like a black box edition of Viraj's repute questions, because there you could see what the program was.
Yes, this
Wanted
is.
to figure out what it was doing, and
Yeah,
now you're seeing the
here's,
trace and it's like, what
yeah.
was the program?
Yeah. So typically what happens is rarely like you have one trace, right? You sort of know the problem that you're trying to solve. So for example, it says bubble sort. So I'm actually trying to sort it using bubble sort. So it gives you a hint. So think of this as someone who has written a program. I mean, if you want to map it back to what was happening earlier this afternoon, earlier this morning, okay? Someone has a program. So in fact, this is what I was trying to do when Viraj was talking, right? Rather than looking at the program, I was thinking of it as a black box. With this input, I get that. And what are those intermediate stages that will get me to that input eventually? Get me to that answer or output. Okay. So shall we move on? You can try this. Please play with it. These questions are for you to solve, and you can submit them if you like. We'll be happy to look at it'll help us understand how effective what we're trying to do is, and so on and so forth, but you don't have to. It's up to you entirely. Okay, maybe there's a way of collecting these. And now we're going to come to the question that was asked a couple of minutes ago. Okay, but before I do that, you can actually draw iterative systems. Okay. So I've got a bunch of points. The numbered, actually, the number is a little small, go from 1, 2, 3, 4, 5, all the way till 14, I believe. Right. Okay. And think of this as a set of points, and the arrow going from one point to another is the dynamical map. It's a function f that's taking you from one to one. Right. So you can immediately sort of look for the pattern in this. It says from every node, okay, there is exactly one arrow coming out. Correct? Now, a node has exactly one arrow coming out, but a node may have more than one arrow coming in. For example, if you look at number 5, there's 2 arrows coming into it. You see that? Yeah. Okay, it's possible. Now, interesting thing to observe here is, first I've colored these points in a different color for a reason, which I'll explain in a moment. But I've only taken a finite set of points. You can have, of course, an infinite set of points, and you can just keep going, like 1, 2, 3, 4, and so on. You can just keep going. Right? This case, notice something interesting. You can come back to where you started, or you can just get stuck in one of these states. Okay, so it's those states that you keep going back to. That is when your program stops. Okay, because there's no point. You know where you're going to go next, right? Okay, so we already know what trajectories are. You start at a point and you keep going. Whatever you encounter on the way is you just keep putting it together and you get a trajectory, right? So for example, if you started with 2, you go to 2, 3, 4, 5, 5, 5, 5, 5. That would be a trajectory. The orbit is nothing but the set of all points in that trajectory. You just collect all the points. So in this case, be 2, 3, 4, 5. Correct? Okay.
Is this why it's important that you have only one arrow going out? Because otherwise,
yeah, we're just
could be
looking at very
ambiguous.
simple deterministic systems. In fact, not just deterministic, but deterministic and total.
No, but he also said that a stopping criteria is that when you keep coming back to
Yeah.
yourself. But if you had another arrow going out, then it wouldn't be clear. Like it would be some
Yes,
kind of
precisely. Yeah,
non-deterministic
precisely.
behavior.
Yeah. So we are going to work in the regime where every state takes you to exactly one state.
One extra
A
step.
large number of programs that we write on a day-to-day basis, in fact, seem to respect this restriction. Of course, it is from a theoretical point of view, it's a restriction because you want to think of being able to go anywhere or nowhere at all, for example.
And you also have a larger cycle.
Right. I could also have cycles. Yes. So I could have cycles that are just of size 1, but arbitrary size.
But that's not a stopping criteria. If you
No.
visit a state, you've
No.
seen
We are only
before-
interested in getting back on one step back to itself.
Okay, right.
Okay. Yes. Yeah. But those kinds of cycles are interesting in other domains when you're doing concurrency and so on, liveness and things like that. Okay. But yes, please.
So we have to remember the state we are, so that then only we can do that.
Right. We need to know where we are. The question is, we need to remember our state so that we know that we've come back to the same state. Yes. And that's why you have variables. Yeah.
For example, like in a Fibonacci series, the number starts from 0, 1, 1, 2. So here 1 is repeated twice, but it doesn't mean that the sequence end here.
Right.
So
But
what
that you're only seeing the trace of Fibonacci.
Huh.
Remember, this is not the trace.
So
These are
these are-
trajectories. we're seeing.
Okay, got it now.
That's
Yeah.
it. It's a very good question. The question is the trace might repeat, right? But the trajectory need not. Yeah. Okay. Right. We're playing this game on states. Yeah. Okay. So now we'll come to the point that was earlier raised. Okay. Points are nothing but states, another name for states. And we talk about something called fixed points, a certain category of points or states, which is X is a fixed point. If you're an X, you apply F, you come back to X. You're right there. You haven't moved actually. You're fixed. You're stuck. Okay. So you're fixed. The opposite of fixed is transient. You're at X, but you apply F and you go somewhere else. Okay, now that somewhere else might eventually bring you back to yourself, but you're still transient. Okay, if you're not fixed, you're transient. Okay. Now it's possible, on the other hand, that you started with a point that is transient, keeps going, keeps going, keeps going, eventually hits a fixed point. Eventually, you don't come back to yourself, but instead you come back, you go or end up at a fixed point. Right? So X is finitely convergent. That means after a finite number of applications of F or finite number of iterations, okay, you reach a fixed point. Such points are called convergent points, or finitely convergent points, which is going to use convergent as opposed to asymptotically convergent points. We're not going to talk about asymptotic convergence. We're just interested in finitistic convergence. Okay. So collect all the fixed points. Of course, that depends on F. F decides how many fixed points it's going to have. That's fix of F, that's just a name. Con of F is set of all convergent points of F. So you've got fixers and conmen here, looks like. Okay. Okay, now example. Take that same graph that you had. What are all the fixed points here? Just by looking at it, you can tell me the answer. Just 5. Okay. The transient points are all the points except 5. And the convergent points are the blue points that get you to the fixed point. Notice the others, the green and the red, there are no fixed points there. All the points are transient. Okay. So that was the reason for coloring them. Yeah.
Distinction between green and red?
Yeah, that was the other question. There is a, so it's just a set of points. The red ones sort of eventually merge with them. So there's nothing other than just a visual cue there, nothing else. Yeah.
So
You can sort of seeing the red. So what's happening is you have these streams that sort of come and merge. They don't diverge, but they come and merge. So they're like, tributaries that come to a main river.
So is it true that every state has to be either itself
Fixed.
a fixed point on a cycle, or a point that eventually reaches one of these things, a fixed point or a cycle, right?
No,
Because-
you could just have 1 going to 2, 2 going to 3, 3 going to 4.
Okay, in
and
a
on.
finite
Yeah.
system.
Yeah,
Right.
finite, yes. Yeah.
Mm, yeah, okay.
But there's no such assumption with the X in the general case.
That is true.
But in most other cases, many cases you can work with finite graphs, for example.
Right, that's
so
what I
on.
had in
Yes,
mind with
yeah.
the out degree 1 condition. you
True,
have
true,
to
true.
do
Yeah,
back.
but what is important is from a given state, you go to exactly one other state. This is the model. This is the regime we're going to work with. And we're going to see, maybe we can solve several problems, and maybe there's some problems we can't. I mean, some problems are inherently non-deterministic, for example. Then we'll have to do something about them. Okay, so let's move on.
So last question, in a finite system, it's easy to identify all the convergent
Yeah,
points.
it's
right?
in general.
BFS or something.
Yes, there are some very famous problems where you just can't hope to get. Okay, which is the fixed point is not a trivial problem to solve. Okay, we're just eyeballing this example and saying, hey, that's a fixed point over there. Okay, that's okay. That's okay. Okay. But the general criterion is if X is equal to f of X, then it's a fixed point. So all we're going to do is check for that. And if
But the
we, if,
convergent points will still have to answer the.
yes, and we're going to do that now in a moment. Okay, the question is what happens to the convergent one? Well, we have to get towards a fixed point, hopefully. And of course, we don't, we're out of luck. Okay, and we'll see what out of luck means. Your program running into an infinite loop is being out of luck. Yes.
So what will happen for the program like those are in green and red dots? Because
They-
for blue one, we know that it will eventually stop at 5. But
Yeah.
for program like this, how
Right.
will
You
it
could, for
stop?
example, keep a collection in your bag of all the states you visited. And would say, hey, you know what? I actually visited one of these. I'm not at a fixed point, but you know, I came back here once. And then you can say, look, if I visited a state already visited, you do this all the time when you do, what is that called? Graph traversals, right? You keep track of visited. You keep track of a subset of points called visited points. And I keep checking, right? That's all. Yeah. So you can figure out cycle detection and graphs and so on, right? Okay. Okay. So exercise, in the examples you had, the 2 traces and whatever else you wrote along with it, identify the fixed points, transient points, and convergent points. Okay, you can try that. Okay, you remember you wrote down the squares example, you don't have it in front of you. The function is very simple. 2 variables in square v and d, v goes to b plus 2, d goes to d plus v, or d dash equals d plus v and v dash equals v plus 2. Okay, and you can start wherever you want, n cross n, and just play around with this and see when would you ever be in a situation where you don't make any progress. In other words, would you ever have a situation where the ball would not fall? Or, yeah. Yes, doesn't seem reasonable, right? So what can one conclude from that? Are all the points fixed? Are all the points transient? Is there a fixed point? Right? So it's possible that I give you an iterative system that has no fixed points, some fixed points, infinite number of fixed points. All of these are open. Everything's on the table. Okay? And likewise for the transient points. Right? So depends, and it's not in general easy to analyze these things. Okay, but we're not getting it. We're just learning the vocabulary. Just because you have the vocabulary doesn't mean that we can analyze everything. Okay? But it's important to have this understanding, this distinction we're making between different states. Some states are fixed, some states are transient, some states are convergent, etc., etc. Okay, and what is, to keep reminding ourselves, what has this got to do with programming? And soon, hopefully, we'll start seeing programs. We've not seen a single program yet. I'm 2/3 into my talk. Okay, now we will. Okay, so I'm just going to sort of have you write down that example, write down those questions, and then maybe you can get to it later on. Okay.
So
Yes,
just
please.
as a sanity check, no transient states is kind of boring, right? That's just every point is a fixed point.
In which
If
one?
you don't have any transient. If
You
nothing
have to
is-
have, sorry, what is it?
So
again?
you were saying all examples are possible, and
Ah.
in particular, if you have to make a system with no transient states, then
Every state is a fixed point.
is a
Take,
fixed
take
point.
all the
That's-
points, have
has
arrows goes into
loops on
themselves.
it.
Yeah,
Right. So that's a
Yeah,
valid
entirely-
system, but that's the only one, right?
entirely legitimate system. Yes.
But there's a unique system with no transient points, but the systems which have no fixed points are much richer.
Ah, good point. Yes, good one. So, right. Okay. So now we come to this idea of iteration. Remember, we started with iteration. Now we know fixed points. Now we're going to study this thing called fixed point iteration. Fixed point iteration. What is fixed point iteration? In English, all it means is repeatedly do something. What is that doing something? F. Till you reach a fixed point. That's fixed point iteration. How to transform the state at each step? how to go from from x to f of x, or how to update your state. The colon equals is not used in Python, but it's used in some older languages, like Pascal, for example. Okay, but you're assigning the state. Okay. And when do you stop? Remember that was a question. When do I stop? X is equal to f of x. That's when you stop. You just stop when there's no point in going further. Because, hey, you're just going to keep getting the same thing in the trace. I know that. How do I know that? Because my f of x is just giving me x itself. So can I, based on this, write a program? Why not? This program is called loop. Takes x and takes f. Okay, notice loop takes x and takes a function x to x and gives me an x. What does it give me? It assumes that the x coming in is in con of f. That means x converges, and it returns a fixed point that is reached by x. So while loop of x comma f is while x is not equal to f of x, x is updated to f of x. That's it. And when you're out of, hopefully you're out of the loop, because remember you assume that x is convergent. When you come out of that loop, you simply return x. Now this is the only while loop we're going to write. We're not going to write any more while. Remember all those examples we had in the afternoon, we had all these morning, we had all these while loops. And my brain stops working when I see a while loop. So I'll just leave one while loop in my program and shove it somewhere in the background in some library, and then not worry about while loops.
So can you explain the syntax in the very first line of it's just a signature?
Oh, the first line is just a comment.
It's a comment. But
Yeah, it says loop is a function. It takes two things whose types, right? So I'm very sensitive to types because everything has a type here. Although Python itself doesn't support types, but I like to think in terms of types. Okay, and I like to think in terms of maps. Each function takes something, that something has a type.
Okay.
In this case, a type is a product. It's taking an x and an x to x.
Right.
Okay, so the x is just the variable x, and the function is f, and it returns something in x.
Sure.
Okay, so if you look at the comments further down, the assumption is that x is transient. Okay, sorry, x is
in convergence.
convergent. Okay, and then you keep applying this. As long as you're holding a transient point, keep updating it in the hope that you will reach a fixed point. That's it. Okay, so that's fixed point iteration. All the while loops that you see in programming, most of them are actually trying to do just this. You can write them like this. If you write the appropriate f, then you can just strip off that while loop, because this is the while loop. It's already given to you. Okay, it's like object-oriented programming. Think of f as a method. You just write f. I'll take care of the rest of the machinery. Okay, yeah. Okay, so now imagine you have a function that takes f and gives you another function. This is called functional programming, by the way. Okay, taking functions and returning functions. And believe it or not, you can actually do it in Python very easily. Okay, so you're taking a point in con of f, and you're returning a point in fix of f. You're just letting it go, letting it go, letting it keep running it. You're guaranteed a fixed point. Why? Because you just started from con of f. Okay, so think of this as f infinity, because you're not really applying it an infinite number of times. It's just a convenient name. Okay. Limit n tends to infinity f of n of x, which means keep increasing your n. At some point or the other, you want to hit the fixed point. Okay. Of course, it works only if you're starting with a convergent point. Okay, now here, by the way, that function f infinity is called limit map. Okay, it's called a limit map because the dynamical map was f, and this would sort of run it all the way it can, all the way to the limit. Okay. So what does this function do? Remember, we are building a small library for algorithms, for iterative algorithms. We saw the first piece of that library. This is the second piece, which builds on the first piece. Okay, what does this do? Limit map is this function that takes a map f, okay, and returns a function that is expecting an x that is going to be convergent. And for those x's that are convergent, okay, it's going to take you to the fixed point. It's like limit map is this bus you get onto. You're convergent, you have that ticket for convergence, it's going to drop you somewhere. If you don't have that ticket, you're just going to go around, looping around. God knows where you go, but you're never going to get off the bus. Okay, so it's one of those dangerous buses you catch, you never can get off. Okay, so that's limit map. I think there are lots of questions in the chat and we should start looking at them. Okay, fine. If any questions, yeah. I'll be happy to.
Maybe just inspired by the question in the chat, which was basically about the notation X maps to X.
Okay.
I think earlier you were mapping from a state space to an observation space and you called it a projection.
Yeah.
But at some point, I think you switched to X to X. So is it important that the domain and the range are the same?
No. Hold on a second. Which
When you were talking about the types and so on here.
yeah. So loop is taking an X and a function that works on X.
So the function maps elements of X to elements of X.
Yes. Yes.
So in the example of
Yeah.
squares, you were
H took
mapping
states to observations, whereas
Right.
F maps states to states. That's an
states
important
to
distinction.
states. Right.
It's a very critical distinction, as a matter of fact.
Right.
They serve two different purposes.
Yeah,
It's
because they do
different
different
purpose.
things.
Right, right. So here, okay, so you
The dynamical map knows nothing about observations, nothing at all.
And like you said, for convenience, we just think of the observations as
Yeah, think
projections
of
when
this
we
as
have
two
to-
dimensions, right?
Right.
The F is taking you this way horizontally. The H is always projecting you downwards,
Right.
right? So just, they don't know about each other.
Right. So the
Right.
edges are just.
Yeah, in fact, that picture I had about, where was that picture? Somewhere here earlier, we had the two of them. Yeah, that was the idea. Okay, so let's move on. So what have we done so far? We've got this thing, this creature called limit map. Okay, now we're almost there. Okay, so example, suppose I take the factorial function, okay, which we just wrote a few minutes ago. Okay, you can hazard a guess about what the fixed points would look like. Okay, you can even show that this is a fixed point. Okay, you can also hazard a guess about what are the points that are going to converge. Again, you can actually show that every point you start in the state space is going to converge. It's going to get to a fixed point. So you can define this function, and in fact, this is also something that you can guess and then, of course, try to prove using induction, because you all know mathematical induction is if I start with an arbitrary point I comma a, I will end up at a times I factorial. In fact, you use this idea to prove that the factorial function works. Okay, but that's another story. Okay, so you can play around with the factorial. It's, again, I said the examples are deliberately extremely trivial, simple. Okay, so that we can focus on the vocabulary, the concepts, and then cook up our own examples if you're not happy with these. There's no shortage of examples ever. Okay, so we've done all this so that ultimately we want to do algorithmic problem solving. What is algorithmic problem solving? Somebody says, I have a problem, solve it for me. Use whatever you want, Mapcode, computers, Python, whatever it is, solve it for me. But what's the nature of this problem? Okay. They're all here. Yeah, I've given you the answers, right? I mean, all the answers are there.
Corner F contains fix of F.
Yes. Yeah. Fix of F is always a subset of corner F. Yeah. Every fixed point is a point that converges to itself. Okay. So it's not. No. I know what to do with this. I always have this problem. I'll take this away, hide them here so they won't roll. Yeah. Okay, so let's move on quickly now to this thing called algorithmic problem solving. Remember, I talked about algorithmic program development, and what is an algorithmic problem? So what is algorithmic problem solving? Okay, algorithmic problem says, well, solve this problem for me, but can we first start by saying, what is the problem? What is it that we want to compute? Okay, so about computing, right? So what is it that we want to compute? So can you specify the problem for me? Okay, so not only are you specifying the problem, we're also making an assumption of what operations do I have at hand. What can my computer do? Can it add? Can it multiply? Can it divide? Can it subtract, etc.? So this is some primitive data types, integers, whatever it is, whatever they are in your language. You have some primitive data types and some operations on them, right? So we just assume some data types. And then, of course, the big question, how to compute, right? Okay, so let's start extremely systematically. Okay, and this is what we'll start revealing, this Mapcode methodology of doing things. So Mapcode methodology is a series of questions, okay, one at a time, right? Trying to uncover one piece at a time of this whole sort of solution, if you will. So the first question is, what is the type of problem we're talking about? What is, to me, what is an instance of a problem? Suppose I ask you to sort an array. What do you think would the instance of that problem be? Well, obviously an array. Suppose I ask you to compute the factorial of a number. Okay, a natural number would be an instance. Suppose I ask you to find the maximum in an array. Again, the instance would be an array, right? So what is the type of the problem instance? Okay. Obvious first question, and let's just call that I, for instance. We'll call that the instance space. That's the first step in Mapcode. But the natural question is, what is the type of the answer? What do you want? We want to find the maximum of a non-empty array, let us say. What I want is an element. Suppose that array is an array of numbers. I want a number. Okay, so that's called the answer space. Simple. Notice how we're decorating everything with a type or a set. Okay, and we're going to work with maps now. So what is the thing that I want to compute? Maybe I can express it as a map, right? So if I have an array, right, I want another array, right, to sort. If I want to sort, if I have an array and I want to pick a maximum, I said array of integers, and the answer is. So I have in my mind, I've not yet realized it as a program, but in my mind, I have a function that I want to compute. I'm trying to, so the model here is the framework here is you are trying to compute functions, right? Just because you know of a function doesn't mean you know how to compute it, right? So computing a function is different from specifying that this is a function I want to compute it. Okay, like I can say factorial, but I'm not told you how to compute it. Correct? Yes, please. Yeah. The mic, yes.
Thanks. So when I say factorial, I mean that will only be sufficient, assuming that you and I agree that yes,
yes.
there is this definition. So
Yes,
what are you looking for? I mean, what is a suitable level of detail for answer to step 3? The question that you're asking.
Very good question.
What are you looking for?
Yeah. In fact, it's often the most misunderstood part of a software requirement. Okay, so people have difficulty. Suppose I'm the software client and you're writing some software for me. I will be unable to specify what this function is. Just, I mean, we're going to spend months and months and a lot of money perhaps just trying to get to solve that problem. Okay, which is a trial and error. We'll build some function. They'll say, no. They'll say, no, that's not what it is. I want this. And so I've just sort of abstracted this into one step. But it's a great question because this often is the crux of requirements. And writing requirements is a huge challenge. I mean, I'm just talking about simple functions from numbers to numbers. But imagine you have some big organization that wants some system to some ERP system. I mean, you can imagine complexity of software. Yeah. So we're just going to assume for now that you and I agree that there is a function. We know what factorial does, but we don't know how to write it yet. We don't know how to compute it yet. Okay. Why we need to agree on this is because when I write the compute function, when I write the program to compute it, we should be able to measure it against something else. We'd like to know whether it's correct or not. So it's correct with respect to what? With respect to the intended function that you wanted to implement. Okay. Yeah. Okay. So what are the primitive data types that you have? Do you have, I mean, what do you have? Increment, decrement, multiply, divide, etc., etc. Okay, I'm also glossing over, by the way, on some very important issues. What kind of operations, how do they compose, all those things. I'm just going to put them on the back burner for now. Okay, I'm just going to assume that I give you some operations and you're just going to use them in a certain restricted way. Right? I mean, can you create those operations and create your own loops around them? Okay, all those things I'm going to simply skip. Okay, now take the factorial problem. Okay, I can say, well, my instance space is n, my answer space is n is natural numbers. My specification says, hey, you and I know what factorial means. We're just going to say that, just factorial. What are the machine data types? Natural numbers, and the primitive operations are decrement, multiply, add. I mean, maybe decrement and multiply are enough for now, so we'll just work with them. Okay, so notice what we're doing. We're just peeling down our computation to the primitives, to our specification of what we want. We're just getting into a very systematic way of writing everything down. That's really what it is. So now maybe you know how to do multiplication, compute the product of two natural numbers using subtraction and addition. You might have done this long ago. Okay. Just write down the problem specification. I take two numbers, maybe natural numbers, just to keep everything really, really simple. And I want to get another number. So my instance space is n cross n. My answer space is n, and so on. You get the idea. GCD is another example. So you can spend a few minutes trying to do that if you wish. Okay. Or in the interest of time, you can write this problem down. We're going to post all of this stuff. So you'll get the problems. You'll also get a Python notebook link on which you can try them out. Okay. So I'm just going to proceed with your permission. That's what I said. So you in the specification, you could say, this is a problem I want to solve, and here are the primitives. What I've not sort of hidden underneath here is I'm not told you how you can actually compose those primitives. I mean, can you actually have a loop and so on? You get into all those, issues about primitive recursion and things like that, right? But I want to just sweep that under the carpet. Okay. Yeah, you're not allowed to use recursion there, for example. Okay. Okay. Now let's get to the solution. What does the solution look like? I want to build a solution. I need program variables. I need some variables to work with. That's my state space. Which variables I choose is up to me. Whatever I need to solve the problem, I'm going to call that the state space. The space of all values, possible values of all your variables constitutes your state space. Sorry?
You're also specifying types. So that's just like naturals.
Yeah, so X could be n cross n or n cross b if it's a Boolean, or if it's an array, it'll look more complicated. Array of, let's say, doing arrays of strings, then it's going to have some type, but yes, some set. Okay, think of types as sets for now. Okay, so for state space for the factorial, we just talked about it. We normally write down a state vector because you have a variable called small x. We say it has components, just like you would write it in a program, right? You'd say I and A, and you tell them what I is. I is typically called the index, and A is called the accumulator. Okay. Okay, you can try to write this for multiplication and GCD. Now you're starting to build the solution. Okay, so maybe you don't know exactly what the variables are. Okay, but maybe you're going to try something out, but at least it's encouraging you to think in a certain systematic way and say, you know what, my variable space is this. Maybe I need 3 variables, maybe I need 2 variables, I need something. Let me just write that down. Very important. There's no shortage of variables. You can use as many variables as you want. Okay? What are you going to do with them is the next question, right? And that question is, before we get to that question, what are you going to do with these variables is, I mean, you can do them in any order, but these are the steps. Okay. Remember, we're talking about a problem instance, and you want to map this problem instance to, you want to start somewhere, your initializing of the variables, right? So I give you a problem instance. How do I initialize the variables? What's the connection between the problem instance and the initial values of those variables? See, imagine you have your program written up. All we're trying to do is refactor your program so that you can think in a very modular, systematic way. Maybe your initialization is strewn across several lines somewhere here and there. We're just saying, okay, turn it into a function, take the input instance, and then spit out a value, give me an initial state. And of course, all in the initial state will have all the variables. We're capturing that notion into a function, a map called init map. Okay, the opposite. Remember, you go from the state to, you went from the instance to the state, now you go from the state to the answer. Okay, think of it like the projection function H. Okay, you go from the state space to the answer space. Often it's a projection, almost always it's a projection. Doesn't have to be. It's typically the X is a fixed point. Yes, that's the idea. Yeah, that's the story. Okay, but we're trying to sort of pull out each actor separately and then put them together, and then they have a party. So, okay, so we can work out the details for factorial. We've got the instance space, we've got the answer space, we've got the state space. Notice all those spaces, and then you've got a bunch of maps. The init map. Okay, init map says if I want to compute the factorial of n, initialize my state to n, 1. The I is n, the a is 1. We all know this, but we're just trying to abstract this into a function now. Similarly, I've done everything. I've got my state space. The answer is sitting inside that state space. A is the answer. A stands for answer. So pull it out. That's pi. Pi just pulls out A from I, A. Right there. Right? I'm sorry?
Where's the action happening on this slide?
No action yet. This is just putting the setup exactly. The stage is being set for the action. The action is going to now arrive and enter. Okay, there is the action. Okay, program map, dynamical map. Okay, it tells you how to move in that space. Okay, we say F acts on X, which means it takes something from X and takes you to another place. Think of F as a bus. You get onto the bus, it drops you off somewhere in one step, then go somewhere else, and you. Because if you sit in the bus for enough stops, maybe you'll get where you want to. Okay, so let's move on. I want to get to factorial. Remember, that's the goal. Okay, so okay, now this you know because we already saw this example. There's nothing to say here. You know this function. You can also program this in Python very easily. Not a problem. So I'm not going to spend any time. Okay, now we have something called the execution diagram. I've got all the pieces. And they're all going to work together. So this whole machine, all the pieces are going to come together. I'm going to create this machine called factorial. Okay, so it's a complicated diagram. There are lots of pieces, but I can go through these pieces. Okay, look at the top left side of this picture. It says instance. You're trying to compute 3 factorial. So 3 is the instance. Follow the top arrow that goes to the right. That's the answer you want. From the instance is 3, the answer is 6. That is called F, the function. It's an instance of the function. Okay. Now, that's what you want, right? That's where you want to go. But here's this bus route doesn't go. There's no direct bus or direct flight to Gandhinagar. What do? You go through some other place, keep going, and then eventually arrive at Gandhinagar, right? So from 3, you don't just jump to 6. Okay, you got to take this detour to 3, 1. You enter the state space, right? And then just keep hopping. Okay, so the thing that takes you from 3 to 3, 1, which is an initial state. Okay, also by the way, a convergent point, as you will see in a moment. Okay, is rho. Rho is a function. It's the init map. It initializes. Its job in life is to initialize. Okay, once you're at that, the F. Remember the F will just keep chugging along. Okay, from 3, 1, it's going to go to 3 gets reduced by 1. I gets reduced by 1. A prime becomes, the new A is the old A times I. So that's 1 times 3, just 3. So 2, 3, 2, 3 to 1, 6. 1,6 to 0,6. What happens at 0,6? You hit a fixed point. You do an F, notice you're just back at 0,6. Okay. At that point, while x not equal to f of x, you're in that loop, but now x is equal to f of x. So you get out of that loop, you get off the bus. Okay. You reached it because you got a fixed point. And when you've got the fixed point, you're actually holding the answer in your hand. Just pull that answer out of your hand with pi. Okay. So to get from 3 to 6, I have to go through this, take all these bus rides that get me there. Okay. That is the anatomy of a computation. All those pieces. So if I'm going to write my program, my iterative program, maybe I should have a row, maybe I should have an f, and maybe I should have a pi. And notice, by the way, the f infinity is just this, just take this leapfrogging all the way from 3, 1 to the fixed point. Because that's what it does, right? It takes the convergent point and maps it to its fixed point. By the way, if the point is convergent, it has a unique fixed point. It's trivial to see that. So f infinity is supposed to do that. So if I had rho and somehow I had f infinity, which I do, by the way, I just showed you how to get infinity, the limit map. I have pi, these 3 things defined, I have the algorithm, right? You define these, of course, define them in the right way, then you get this. I'm just telling you the pieces. I won't have enough time to tell you why what I've defined is, in fact, I won't be able to defend in this talk what the rho, pi, and f that I have. That's for another workshop, okay? Some other time. Okay. So I get put into an initial state, which also happens to be a convergent point. I keep chugging along with f's. I reach a fixed point. I get off the bus using pi. I'm holding the answer. Okay, so here's an exercise. Draw this question. Okay, let's move on. Exercise for you to take home. Do this thing for multiplication and GCD. What's the instance? What's the answer space? What's the f? Well, f is multiplication and GCD. What's the row? What's the state space? What's the row? What's the f? What's the f infinity? What's the pi? You don't actually have to worry about f infinity. I've given you this library that just does the f infinity if you were in the right place. Okay, so you don't have to just have to define f. You're going to get infinity. Okay. Yes, yeah. Yeah, otherwise you're out of luck, sorry. Okay. Okay, so now I built myself a machine, right? I built myself a machine. All these pieces together give me a machine because you want factorial of 3. I'm going to crank this machine. It's going to run for a while, lots of steps. It's going to give me this answer. Right? And forget about this algorithm and computed by, I'll just skip that for now. I'll just summarize here for you the 8 of the 10 steps that Professor Viswanath has in his book on Mapcode. Okay, it's just a checklist. So make sure when you're writing your code, you have those 8 points. I'm sure you're dying to see whether this thing actually works or not. So we should actually run some programs. That's what we're going to do next, from design to code. Okay, there are 2 other conditions which are correctness. I'm going to write some code for you based on a design, but I'm not going to justify why it actually works. That's part 2 of this talk. We don't have time for that today. Okay, so let's go from design to code. So I'm going to skip this. No, sorry, where was that? Something is wrong. Give me a second. No, I'll just skip to, it's time to go to code. That's what it is. I won't find those slides here because they're code. Okay, so what I'm going to do now, I have just a few minutes left, 5 minutes. Yeah, so I'm going to switch to sharing my laptop, which is running a Python interpreter where I'm going to just take all this code and show it to you. Okay, so how do we do that? Go to Zoom. We say, go back to meeting, stop sharing. Strange. Stop share. Yeah. Switch to this. Share desktop. Just switch to my buffer. Okay, so is that visible to everybody? I'm going to show you piece by piece the things we're talking about. Okay. So what is it that we wanted to do? With this function loop, it just loops. Okay. I don't know what's there. Just one of them is enough actually. There's just two different ways of writing it. But this is limit map. Okay. This is code that we just saw a few minutes ago. So this is actual code sitting in a Python buffer. And now let's look at Mapcode, the Mapcode combinator. This puts everything together. So Mapcode is very simple. Remember the row and the F and the pi, you take them together. Okay. You have all the conditions, right? F maps X to X, row maps I to X, and the sorry?
This is your bus ride and the return statement, like row of I.
Yeah, so that is essentially, you're taking the row and F and pi, and you want to construct, put them all together. So what do you want to do? You want to take an instance I, row of I will get you to an initial state, which is convergent. You keep applying F till you get a fixed point, namely you apply the limit map, F infinity. You build that from F, okay? And you keep applying it, run it, okay? So you take I, you apply row on it, you're in the initial state, you apply F infinity, you reach a fixed point. Of course, lots of Fs are being iterated, F is being iterated many times, and then you pull out the answer, pi, you're done. As long as you've defined these three functions correctly, code should run, correct? Now, how difficult is it to define these? The hard work is done, the F infinity, limit map, all that's automatically done, the looping. So let's look at factorial, okay? So I've got the three functions, right? What are those three functions? Row, F, and pi. Row takes n and creates a tuple. My state vector now has two values, n, 1. Pi is very simple. It just takes I and a. I mean, X, just pattern matching in Python. Okay, and just returns a. What does F do? F is just 5 lines long. Right? First line is pattern matching. I mean, the second line in the body. And if I is 0, that's a fixed point. You just return X. You know it's a fixed point, right? Because you're just returning X. Otherwise, decrement I and a times I. Okay, that's it. So you got the row, you got the pi, you got the F. Now it's time to pull out Mapcode, right, from the hat and use it. This is where you use Mapcode. Mapcode essentially composes all these three things and gives you the answers. Your factorial program is 1 line long, provided you define the row, F, and pi, and Mapcode.
Any program will be 1 line long.
Yes. Any program could be 1 line long because the lines, how many characters in a line don't matter. Okay. Unfortunately, in Python, they do because you run out of margins and you have all kinds of messy things happening. But so I'm sort of forced to.
I think the functions do all the hard work for you.
Yeah. So once you define, it's like, as I said, it's like defining methods in object-oriented programming. You define the methods, the machinery does the rest for you. That's the nice thing in object. It's really modular. You don't have to think about, okay, when does it get called? What does it get called with? Who's calling it? You don't have to think of any of those things. Okay. So now let's try to run it. Oh no, no scratch. Python. Okay. So I just imported, what is that? I just imported that factorial. From factorial import. Factorial is just this file right in front of you. Run it again. I don't know what happens if we run it again. I don't know if it did anything or not. Maybe it did nothing. Okay, and all I have to do is this. 0, let's start conservatively. 1. So far, so good. Getting better. Yeah, maybe it works. Yeah, I'm just lazy. Okay, so I've just given you one example, just one, of how all these things, all the machinery sits around a simple program called factorial. You can take any program you want and try this out. I mean any program you want, any algorithmic, any program implementing a sequential algorithm, and try this out. Okay, I'm going to stop here. There's actually plenty more to discuss, but I have 0 time. I'm out of time. Okay, 3:33. Welcome. Okay, just to remind everybody, you will have this material on some site somewhere soon, which will be on that group.
You also had a feedback form you wanted to.
Yes.
tell
So
us?
let me put that up. Sorry, I'm supposed to put that. Did you post that or? Okay, maybe you can just post it. I do want to thank Mrityunjay. He's worked on lots of the examples of Python, other stuff. Professor Viswanath, who is my colleague, sits a couple of doors away from me. Lots of discussions about this. In fact, that's how I got inspired to learn about this. And it's quite fascinating. It was, to me, the greatest introduction to theoretical computer science I've ever had. Just that book. And all of you for the nice questions, lots of interesting questions, for participating in this. And of course, Nidhara for hosting us. Thank you so
Of
much.
course, yeah, it
Thank you
was-
so much.
the
And
pleasure
ACM
was
for
ours.
supporting us. Thank you so much. Okay, time to leave.
So we probably have just a couple of minutes for a quick question or comment if anybody has one from the online audience or from here.
Yeah, just get out of this meeting now.
All right, so yeah, just to reiterate, I
So
think we will
actually,
be.
Neil, can I just? right,
Yeah,
sorry.
of course, please.
No, so this is just more a comment I've already shared with Venkatesh and Mrityunjay, but just also wanted to share with the rest of us. So I've been trying to use this in this course that we run at IISc, trying to see how students react to it. And of course, their first approach is, why are you doing all this rigmarole, right? I mean,
Right.
factorial, I want to write straight away, right?
Right.
And so we tried to, together working with Mrityunjay and Venkatesh, we tried to sort of show them its generality, that, you know, the same formulation with just a different function f can create all these different solutions, but, you know, there's the same underlying philosophy or approach, right? And I guess so that's the comment part.
Yes, thanks.
And I guess
Thanks. It's true.
the more open-ended question, and I'm not asking you for a definitive answer, but what I would like to know is, like, pedagogically, do you think that's a good way of introducing this? I mean, you know, because otherwise people will, I think, will have a reaction to this, that, you know, what's the payoff?
Yeah. So great question. I can take a shot at that. So the way I look at it is, if I were to teach theory of computing, this is where I would start. This would be my introduction to the theory of computing. From there, you could go to Turing machines, you could go to push-down automata, you could go to formal languages. But to me, this is an extremely valuable theory of computing, because I can identify pieces of my program, no less, okay, with elements of this theory. Okay, so there's an immediate payoff in learning this. I don't have to write the row f and pi in my program every time. But as long as I'm conscious that there's a row f and pi, that's tremendous progress. I know there's a force, there's momentum, there's conservation of energy. I just know it. Right? I've never actually tried to measure the energy of something in the world. I've not. Maybe if I was in some other question, but just the fact that I know it influences me in very deep ways.
I don't know if it actually makes things easier to debug if you adopt this as a format or a best practice. It's possible that.
Yeah, projecting
Yeah.
those variables,
Right.
prints, for example. In fact, you had that version of while loop where you printed the state space, right? So you just go, every time you go, you just print X, the entire state space, you like, or whatever you want to print. And I mean, okay, that's the first part. The second sort of the second part, the second answer to what you just asked is honestly, we don't know. We've not tried this out. We don't know what people will say. People say, no, no, you're wasting our time. I mean, if I go to a programmer in Mrityunjay's company and say, sorry, door shut on you. We don't know. But if there are students in the class, like some of you sitting here, I can teach them as a theory of computing. And let's see where it goes. Right?
Yeah, we
That's
can add one more comment to it.
So I think, and again, this is both based on industry experience as well as with IIIT students. I think the more we go in the path of, okay, I have done enough programming, because this is unlearning. I mean, the way I have understood and more I have talked to Professor Viswanath, my understanding has sort of gotten better now. But his point of view is, this is a way of thinking. So now way of thinking can't come too late. So the problem that we have been having when we have been talking about some of these things with people is, since it is a different way of thinking, which seems like a dumb way of thinking because I'm used to it, it's almost same thing I get when I started teaching actually functional programming to people who know so much of imperative programming. It was such a hard time first few lectures just to say, why am I doing all these kind of conversations? So it's like unlearning. So it takes time, and therefore at least long-term view should be maybe before first year. Can it go in like the computational thinking when we are talking about, can we go to 7th, 8th? Because there's nothing here actually, which is not taught to 9th and 10th students. It's like a map,
There's no
function,
calculus.
nothing else. Right? It's much simpler than some of those maths. So ideally, if it goes early, it will be better. If it goes late, it will be harder. But I think it's a way of thinking rather than, I mean, anything else. It's a problem solving. It's a strategy. It's a thought, not programming per se. We are connecting it to programming just to make sure everybody understands program, but otherwise it's not really that.
right. It's a way of structuring your solution, any algorithmic solution. Okay, any other questions? Anything else? Time for coffee. Great.
Thank you so much.
Thank you. Absolutely wonderful. See so many questions about it. By the way, if you wanted to read through the book, I have a copy of the book here. Feel free to browse through it. Oh, the mic. Yeah, I'm not.